Very good morning, students. So, today we are going to see the next three types of black box testing techniques. Yesterday, we had discussed three types of black box testing techniques, which was equivalence class partitioning, boundary value analysis, and decision table testing. Okay, so today we are going to see the other three types. So totally we have 6 types of black box testing techniques. Now the fourth type is pairwise testing. Then we have state transition testing, and we have the other one. The last one we have is, let me see, state transition testing, and the last one is use case testing. Okay, so we are going to see those three today. So in pairwise testing, see every black box testing technique attempts to reduce the number of test cases. So similar to equivalence class partitioning and boundary value and decision table, here pairwise testing also attempts to focus on reducing the number of test cases. Okay. So here what we do is we take each and every input in pairs. Okay, so we take every pair of input and we try to find out the combination of the different types of inputs. For every input that we have, we'll be finding the combinations, and out of these combinations we'll be selecting any two combination after framing a particular table form. Okay, that is, we'll be having the different combinations of input that will be represented in the form of a table, and from the table we'll be randomly selecting any two columns. So when we select any two columns randomly from the table, it will represent all possible combinations of inputs. Input in sense, see, if I have three input data, say for example student name, roll number, student marks, and the category, student category, general category, whatever it is. Okay, so these three can take different values. Roll numbers will be taking values from 1 to 60 in your case, and then you have your marks that will take, if it is your university marks, it will be taking values within the range we have. If it is out of 60, it will be taking values till 60 range. And for category, you'll be having general and reserved category and all those things. Okay, so you'll be having, there are certain values that every input data can take. Okay, so we'll be finding the combination. See, the roll number 1, marks is this, category is this. So that is one combination. Likewise, roll number 2, the marks of roll number 2 and his category. Okay, likewise, we'll be doing the different values. So we'll be seeing examples so that it will be more clear to you. So pairwise testing, otherwise called all pairs testing, is a testing approach taken for testing software using combinational method. Combinational method means we find the different combinations of input data. Okay, so when the number of combinations is very large to test, then the number of test cases that you need to frame and execute will be very large. So we always try to reduce the number of test cases, just because if the number of test cases is more, then you require more time to test. Okay, so we'll be keeping the test cases to a low minimum, and we'll be ensuring that the test cases will have maximum test coverage. So our test cases should be such that it should be lesser in number. The number of test cases should be reduced to a fixed number. It should be a lesser number, and those test cases that we use should cover the code maximum. Okay, so it should provide maximum test coverage, yet it should be reduced to a small number as well. ഓക്കെ, അപ്പോൾ ടെസ്റ്റ് കേസിൻ്റെ നമ്പർ കുറയ്ക്കുകയും വേണം, നമ്മൾ സെലക്ട് ചെയ്ത ടെസ്റ്റ് കേസസ് മാക്സിമം കോഡിനെ കവർ ചെയ്ത് ടെസ്റ്റ് ചെയ്യാൻ വേണം. സോ ദീസ് ആർ ദി ടു intentions behind all type of black box testing technique. All the types of testing techniques coming under black box focus on these two. Okay, reducing the number of test cases and ensuring maximum test coverage. So we have here, we have an example here. So suppose we have a software to be tested. We just got 10 input fields, 10 input data that we're going to provide, and each of those 10 input data can take 10 possible values. Each can take 10 possible values. So we got to have how many? So totally we got to test 10 raised to 10 possible test cases. So in order to test all those input data, wherein every input data takes 10 values, so we need to have 10 raised to 10 test cases. Okay, so that is the exact number of test cases that we require. Okay, and what we are trying to do is, we are trying to reduce this number, 10 raised to 10. We are trying to reduce this number of test cases. So here, another example, if system has different 4 input values, okay, 4 input parameters, and each is taking 3 values. Okay, so I have got 4 input values, and each input value is taking 3 values, 3 values it can take, each input data. Okay, so say for example, my the category of student can take 3 values. One is general category, second is reservation category. Likewise, I can have OBC, OEC, general. Okay, that means that the category input data is taking 3 values: OBC, OEC, general. Okay, so likewise here we have 4 input parameters, 4 input data that is taking a set of 3 values, 1 to 3 values. So we have the possible number of test cases will be 3 raised to 4. Okay, 3 raised to 4. I've got 4 input parameters, each taking 3 values. So it will be 3 raised to 4 different test cases I got to prepare. Now what I'm going to do is, I'm trying to reduce this number of test cases. Now in order to do this, I will be using one table notation called as orthogonal array. Okay, I'll be using a tabular format to represent my input and its corresponding values using a table notation called as orthogonal array. Okay. So in order to represent this orthogonal array, what I'm going to do is, consider numbers 1 and 2. Consider two numbers 1 and 2. What are the number of combinations that we can make out of these two numbers? The combinations are given there. It is 1 1, 1 2, 2 1, 2 2. Yes, out of the two inputs 1 comma 2, 1 and 2, I can have 4 combinations: 1 1, 1 2, 2 1 and 2 2. So I'm going to represent that in the form of this orthogonal array, and this orthogonal array representation is given as L4 2 raised to 3. Okay, L4 2 raised to 3. That means that I've got 4 columns. 4 columns that 4 represent the number of rows. See, I've got number of rows. The number of rows is represented by 4 and 3 represents the number of columns. Okay, this orthogonal arrays notation is given as L4 2 raised to 3. That L4 represents, 4 represents the number of rows and 3 represents the number of columns. Okay, and the 2 represents the maximum value that it can take. The maximum values the input takes is 2 here, 1 and 2. So 2 values. Okay, I am considering 2 values, 1 and 2. So that is represented by the 2 in the bracket. Okay, so this orthogonal array is represented by the notation L4 2 raised to 3. That 4 represents number of rows, 3 represents number of columns, and 2 represents the number of inputs that we are considering. In this example, we are considering 2 inputs, 1 and 2. And we are putting the maximum number of combinations that we can make out of these two numbers 1 and 2, which are 1 1, 1 2, 2 1 and 2 2. Okay, and we are representing it in this particular table. Just see here in this table we have 1 1. See, if I take this particular orthogonal array, I can have any 2 columns. If I take any 2 columns of this orthogonal array, I will be getting all possible combinations. See, if I take columns 1 and 2, just see the values in columns 1 and 2. 1 1, 1 2, 2 2, 2 1, 2 1 and 2 2. Okay, so similarly, if I take columns 1 and 3, randomly I am taking column 1 and column 3. See the combinations in 1 and 3. 1 1, 1 2, 2 2, 2 1. Yes, so it is there. Now take columns 2 and 3. 1 1, 2 2, 1 2, 2 1. So all combinations are possible if I select any two columns of this orthogonal array. So what I do is, out of these, this representation of orthogonal array, for every column, every randomly chosen two columns I'll be selecting, and I'll be preparing the test cases for those two columns. So this is how I try to reduce the number of test cases. So provided I have a set of input data and set of values that each input data can take, I will be having a very large number of test cases required to test all the combinations. But if those combinations are going to be represented in the form of an orthogonal array, then it is like any two randomly chosen columns of the orthogonal array can represent all possible combinations of input data. So what I will be doing is, I will be representing the combinations through orthogonal array representation, and I will be choosing any two random columns in the orthogonal array, and I will be framing the test cases. That is how I will be reducing the number of test cases. Okay, hope it's clear to you. Another example is here. I am taking input numbers 1, 2 and 3. In the previous example, we considered only two input data 1 and 2. Here we are considering three numbers 1, 2 and 3. And the combinations that we have for 1, 2 and 3 is 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3 and 3, 1, 3, 2, 3, 3. Okay, and this we are going to represent in the orthogonal array. So the notation that we have for this orthogonal array is L9 3 raised to 4. That means that we have 9 rows and we have 4 columns, and the number of inputs we are considering is 3. 1, 2 and 3. Okay, 3 values we are considering. The number of rows we have is 9, number of columns we have is 4. Okay, so this orthogonal array has got the notation, is represented by the notation L9 3 raised to 4. Now consider any two random columns from this orthogonal array. Let us consider columns 1 and 2. What are the combinations available there? 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Yes. And consider 2 and 3, columns 2 and 3, 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, 3, 1, 1, 3, 2, 1, 3, 2. Consider columns 2 and 4, 1, 1, 2, 2, 3, 3, 1, 3, 2, 1, 3, 2, 1, 2, 2, 3, 3, 1. So it's like if I take any two random columns from this orthogonal array notation, I can have all combinations of inputs got. So I'll be preparing test cases to test these two columns. Okay, so I'll be reducing the number of test cases to these two columns. Based on these two columns, I'll be preparing test cases. Okay, so this is one way to reduce the test cases, and also I can have maximum test coverage. So my intention behind, not my intention, the intention behind any black box testing technique is to reduce the number of test cases and ensure maximum test coverage. So in the case of this pairwise testing technique, we'll be finding out the maximum possible combinations of input data and their values. We'll be representing the same using an orthogonal array such that any two random columns of the orthogonal array can represent all possible combinations of input data values, and I'll be preparing, based on these two columns, I'll be preparing some test cases so that I can reduce the number of test cases. Okay. State transition testing. Now what is state transition testing? The next type of testing is state transition testing. State transition we have already seen in design patterns. What is state transition? Okay, so state transition in sense finite state diagrams and all we have seen. So in this state transition basically tries to test the states as well as their transitions. Okay, so it will be testing each and every state in which an application can be in, depending upon the occurrence of certain events. Just as we always cite the example of ATM. When you move to an ATM machine, if nobody is there, you are the only person, then the ATM machine will be idle. Then once you swipe your card, then it will be moved from the idle state to the working state, and then once you enter your card, it will be prompting you to enter your PIN number if the card is properly read. So that if it's not properly read, it will display the error message, otherwise it will give you the options. So those are the two states in which the application can be in, provided the user swipes a card. Yes, so likewise your application can be in different states depending upon the occurrence of certain events. Yes. So that is going to be tested, the different states an application can be in is going to be tested by means of state transition test. Okay, so when a system must remember something about what has happened before, or valid or invalid orders of operations exist, state transition diagrams are excellent tools to record the information. So when the application can be in different states depending upon the occurrence of certain events, in order to represent the states that the application can be in, the best possible notation you can have is a state transition diagram. Okay, so testers can provide positive and negative test input, and they can record the behavior. So we'll have testers providing the application with valid input. A valid input is provided, what is the state in which the application will be in. If it is provided with invalid input, what will be the state the application will be in. Okay, so these are the different concepts coming here. One is state, what is meant by a state. And state transition diagram, states are represented by circles. Okay, state is the state wherein the application will be at a particular point of time. So state represents a set of conditions, or it's a condition in which a system will be waiting for one or more events. Okay, and the states remember the inputs the system has received in the past and define how the system should respond to subsequent events when subsequent events occur. These events may cause state transitions or state changes. Okay, so it's like state represents the condition at which an application is at a particular point of time. Okay, now when a particular event happens, event is something that causes the state to change. Okay, so state transitions happen upon the occurrence of events. So in a state transition diagram, states are represented by circles. Okay, and a state transition means state of change. State of change happens when any particular event will happen. Okay, so upon the occurrence of an event, state transitions happen. Now transition is the change of state. Event is something that causes the application to change its state. Okay, event is responsible for state transitions. Now action, that is when a particular event is happening, what is the action that the system is taking? Okay, that is action. Now we have an entry point and exit point also represented in the state transition diagram. See here, example here, when we provide, see, airline reservation system, when a reservation, we are trying to make a reservation. So when you provide the necessary detail, you provide your information in order to book the ticket, you provide your destination, your starting point and everything, and you try to make the reservation, so that the system will be from the idle state, it will be trying to make the reservation. So it will be in a made state. Okay, and you try to perform the payment operation after you have entered your details, travel details. You will try to pay the amount, so that if it is the amount processing, the payment processing is going to happen successfully, then it will cause, as in when the user is going to make the payment, the system will be moving from the made state to the paid state. Yes, so initially the system, when you're providing with your travel information and personal information, it will try to make the reservation. So meanwhile, when you try to do the payment, then it will be processing your payment. The system will process your payment details, and if the payment details are successfully processed, there will happen a state change. There will be a state change. That means that the system will move from the made state to the paid state. Okay. Now here the third diagram, these are all state transition diagrams. The third, see, in the case of third, after the payment is successfully completed, you have the ticket, e-ticket that is given to you. Okay, so here there are three states represented. One is the initial one is the made state. Then we have after payment the paid state. After payment is successful, we have the ticketed stage. Okay, so these are the different states here. See here the next one. This diagram represents time expires and the reservation is cancelled for non-payment. See, if this is the normal flow is there, okay, and see, from the made state we have another one state. That means that you are trying to make the payment, but your payment is not getting processed successfully. That means that your registration will be getting cancelled. You got to try another one more time. Yes, it normally happens when we try to make payments. Sometimes there will be some server error or server will be busy so that our payment can't be processed at times. So if you're trying to make a payment for a reservation and the payment is not proceeding correctly, then it will be failing and your task will be failing. It will be cancelled. So that is cancel state. Okay, so these are the set of states here. And if I myself cancel my processing, then it will be cancelled by the customer. Okay, so likewise different states can be there. Now what we are trying to do is we represent the states using the state transition diagram. For every path that I have in the state transition diagram, I'll be writing the test cases. So after I represent the different states that the application can be in, I will be writing test cases for each and every path in the state transition diagram. Come here. So here we have creating test cases. After representing your application using state transition diagram, I will be preparing the test cases for each and every path. See, path 1, path 2, path 3. 3 paths here in the state transition diagram. So I'll be preparing the test cases for each of those paths in order to test each of those transition paths. Okay, so this is how we are reducing the number of test cases. So for every application, if the application is such that it can be in different states during the course of its execution, when the application is put into use, the application can be in different states and the states are represented by means of state transition diagrams, in which the state transition diagram will represent the different states, the state transitions, the actions, all those things. Okay, so when the application state transitions are represented through state transition diagrams, then I will be preparing test cases for each of those paths in the state transition diagram. Okay, so that is the idea behind state. See, these are the different paths that are shown. Okay, so this is the idea behind state transition testing. So we have covered pairwise testing, in which we'll be getting the input data and the values that the input data takes. We'll try to find out the combinations of all input data and their corresponding values. We'll represent the same using orthogonal array, and every random 2 columns of the orthogonal array can represent your test cases. Then we have the next type of testing, which was state transition testing. In state transition testing, what we will be doing is, in state transition testing, we'll be representing the states as well as the transitions. And this will be represented in the form of a state transition diagram, and we'll be preparing the test cases for every path in the state transition diagram. Okay, so that is done in state transition. So that is all regarding state transition. Now we have got one more testing technique left, which is called as use case testing. Use case testing technique. So we are going to have use case testing done. And use cases mainly represent the scenarios. Okay, scenarios. Scenarios will be representing the actors. Actors will be having actors, will be having scenarios which represent the interactions. Okay, so actions and actors. Okay, actors are the persons who are responsible for the interactions. Okay, so I'll be handling this topic tomorrow. So make sure you go through all these topics and come tomorrow, so that we'll be finishing off white box testing technique as well as use case testing tomorrow. Okay, thank you for your patient listening.